All righty. Okay, the last couple sections in our textbook that deal with IR. 14.6 deals with how do we analyze an infrared spectrum. You know, when you just see an infrared spectrum for the first time, it just looks like a bunch of lines maybe on a page, but there are some steps that we can take to help us to analyze a spectrum. First thing we're going to do is we're going to focus on the diagnostic region. Okay, we're going to start with the diagnostic region. What was that? That was above 1500 reciprocal centimeters. Remember that below that is the fingerprint region. We're not going to worry about that a lot in this class, but we said, okay, double bonds, a double bond, whether it's a carbon-carbon double bond or a carbon-nitrogen double bond or a carbon-oxygen double bond, double bonds tend to show up around 1600 to 1850. We're going to narrow that down even more when we look at the table in a few minutes. Triple bonds, whether it's a carbon-nitrogen triple bond or a carbon-carbon triple bond, there's no carbon-oxygen triple bonds that we would see in an IR. Those are going to be around 2100 to 2350. For example, an alkyne has stretching around 2150 to 2100, whereas a nitrile has stretching around 2260 to 2240, so 2250. And then we said, okay, well, also in the diagnostic region, once you get above 2700, you can look for bonds to hydrogen. That could be a carbon-hydrogen bond, that could be an oxygen-hydrogen bond, and that could be a nitrogen-hydrogen bond. Those are the things that we're going to look at. Then you analyze the wave number. So we look at the wave number in reciprocal centimeters. Then we look at the intensity and shape of each signal in that diagnostic region. Remember that oftentimes a molecular structure can simply be identified from an IR. Not always, but oftentimes it can. Well, let's look at the diagnostic region even closer. And we see that once you get above 3000 reciprocal centimeters, there's a lot of important information that we can get from there. In fact, I like to take my ruler, put it right on the page, and draw a line at 3000, just like I have in red here, and then I look above that line. Now, in any infrared spectrum, or I'd say greater than 90% of the time, you're going to see a bunch of stretching below 3000, okay? Around 2900. This is ubiquitous. This is in all the spectra that we see. And if you're wondering, why do I always see a blob just below 3000? It's because those represent the sp3 hybridized carbon-hydrogen bond stretches, and there's so many different types of sp3 hybridized carbons in most organic molecules that we see a large blob there. However, we said that once you get to around 3100, this is where you see carbon-hydrogen stretching between an sp2 hybridized carbon and a hydrogen. And then around 32, maybe even up to 3300, even up to around here, this is where we see sp hybridized carbon-hydrogen stretching. We talked about primary and secondary amines, and they have stretching, between 3250 and 3550, somewhere in that range. I talked about the difference between the symmetric and asymmetric stretching, and then, of course, oxygen-hydrogen stretching, which we find in alcohols and carboxylic acids. And that is usually the easiest thing that there is to recognize in an infrared spectrum. And we're going to take a look at an example of that in just a couple of minutes. Well, the last section in our book that deals with IR, after this we get into mass spectrometry, the last section that deals with IR talks about the utility of IR. And besides using IR to simply identify a functional group, we can actually use it to monitor a reaction, because oftentimes chemists will do reactions where we convert one functional group to another. Take a look at this reaction here. We're taking an alcohol, and we're converting it into a ketone. Well, if I started this reaction in the lab and I wanted to know if it was done or not, how would I figure that out? Well, you could monitor it using infrared spectroscopy, because for the alcohol, if we run an IR on it, we're going to see that broad oxygen-hydrogen stretching. So we'll see broad stretching from the oxygen-hydrogen bond, which is capable of hydrogen bonding, from 3650 roughly to, I don't know, around 3,200 reciprocal centimeters, I think is what's on our table. We'll look at that in a second. Whereas a ketone, we're going to see the carbon-oxygen double bond stretching in the ketone, which is going to be around 1715 reciprocal centimeters. So we should see the disappearance of this signal and the emergence of this signal from our ketone. So very cool. And in fact, there's even infrared probes that you can put in a reaction mixture. Well, you don't have to memorize every single signal in the infrared spectrum, because I'm going to give you this handout for your quiz. Okay, so you'll have this handout for quiz. We'll call this the quiz 14 handout. You will have this for quiz 14 and any subsequent quiz where I ask you a question about IR. I'll give you this table. And this is just a version of a table. It's like an abridged version of one of the tables that's found in our textbook. The stuff at the bottom, this is from chapter 15. So you don't have to worry about that for this quiz, but I just leave it on here. So I will give you this for your quizzes. However, will not have this handout for final exam. Okay, you don't get a handout for the final exam, only for the quizzes. And the idea is that by the time you get to the exam, you'll have enough experience with IR that you'll have all these signals memorized. Let's take a look at a few of them. The alkane, we saw that ubiquitous, carbon-hydrogen stretching below 3,000, and of course this is an sp3 hybridized carbon. Then with an alkene, we saw that above 3,000, we saw the sp2 hybridized carbon-hydrogen stretching. You also see the double bond around 1630. An alkyne, we see the sp hybridized carbon-hydrogen stretching around 3,300 reciprocal centimeters. The triple bond, the alkyne triple bond stretching is around 2,150 to 2,100. For an aromatic, so an aromatic is like this. It's just an aromatic ring. Well, we have carbon-carbon double bonds in an aromatic ring, don't we? And they have a little bit lower stretching absorbance than an alkene. They're around 1,600. And usually these are actually a collection of 2 to 3 signals. So it's usually 2 to 3 stretches that are from like 1,600 to 1,450. And I'll show you some examples of those. And then, of course, you see the sp2 hybridized carbon-hydrogen stretching, because you have 6, sp2 hybridized carbon-hydrogen stretching bonds in benzene. The alcohol, we've looked at that already. You see that broad stretch from 3,650 to 3,200. Now, keep in mind, if you have an alcohol, so when you have an alcohol, you also have the carbon, besides the oxygen-hydrogen bond, this bond, you also have the carbon-oxygen bond. And so that's a polar bond. And you usually see that stretching in the fingerprint region, but it's usually easy enough to notice. It's around 1,250 to 1,000. If we have an ether, well, in an ether, we have a carbon, an oxygen, and another carbon. And so we see the carbon-oxygen stretching around 1,300 to 1,000. The amine, we already went over the primary amine and the secondary amine, and they have stretching around 3,550 to 3,250. An aldehyde, the carbonyl, you notice that a carbonyl shows up in an aldehyde, a ketone, an ester shows up in a carboxylic acid, and an ester. Yeah, I already covered the ester. Oh, it's also covered in found in an amide. All those carbonyls, you can see that they're anywhere between 1650 for the amide all the way up to 1735 for the ester. So they're usually in the early 1700 region. So an aldehyde is around 1725. What's neat about an aldehyde is that in an aldehyde we have the carbon-oxygen bond, but then we also have a carbon-hydrogen bond. And this carbon-hydrogen bond gives us what we call aldehydic carbon-hydrogen stretching, which is around 2750 and 2850. You usually see 2 little signals. A ketone carbonyl is around 1715. An ester, of course, an ester has a carbonyl So we have the carbonyl, which is around 1735, but you also have this carbon-oxygen bond, which is around 1300 to 1000. Carboxylic acid. In a carboxylic acid, you have the carbonyl, and the carbonyl is around 1710. You have the carbon-oxygen stretching, so this carbon-oxygen stretching here, which is around 1320 to 1210. And then, of course, you have the oxygen-hydrogen stretching, which is the lowest hanging fruit. It's so broad, between 2400 and 3300. And amide, we don't look at a ton of amides, but you should know the amide. So the amide has the carbonyl, but it also has a carbon-nitrogen stretch, which isn't even in here, so I digress. But the nitrogen-hydrogen stretching, I guess, is shown in here. So we have that, and that is around 3550 to 3060. And then the last one is the nitrile, which has a triple bond between the carbon and the nitrogen. I just say it's usually somewhere around 2250 reciprocal centimeters. Now, again, that's a lot of information that I covered quickly, but you're going to have this table with you when you take the quiz. Now, it can't be a table that you've got all kinds of crib notes written on like this. You have to just bring in the blank sheet, printed, fresh, with nothing else on it. Show me the front and the back, and you're allowed to use that on your quiz. Okay, so the first exercise we're going to try, and these come straight out of Klein, is, no, that's not it. It's these practice problems here. We're going to start with question 14.9. We'll start with something that's relatively not uber complex. It says, for each of the following IR spectra, identify whether it is consistent with the structure of an alcohol, a carboxylic acid, or neither. So an alcohol, that means you've got ROH, so you're looking for that OH stretch, or a carboxylic acid, so that means you're going to be looking for a super broad oxygen-hydrogen stretch, or neither, means none of those. So let's start with A. If we zoom in on A, what do you think? Is that an alcohol, a carboxylic acid, or neither? Could anybody answer this one? Might need the ruler here. You can see that we've got a really broad stretch here. Starts right around, kind of here, and it kind of ends off somewhere around here. Yeah. So that means its range is somewhere around, around 3,100 to, I don't know, about 3,600 reciprocal centimeters. So what is that, Angel and Kiana? Yes, it's an alcohol. So this is an alcohol. Alcohol. This is the oxygen-hydrogen stretch. It's very broad, isn't it? So there we go. So we've identified an alcohol. If we go down here, let's go over to C. Let's do C next. What about C? We see this gigantic stretch. I mean, this thing is humongous. And if we bring the ruler in here, you can see it starts all the way down here, something like, oops, that's not right. Something like this. And then it goes up all the way, something like this. It's all the way from, this is an oxygen-hydrogen stretch from 2,400 to about 3,400 roughly reciprocal centimeters. So yeah, absolutely. This is a carboxylic acid. Carboxylic acid. And what else do we have in a carboxylic acid? Well, we have the carbonyl and we have the oxygen hydrogen. So that's this here. But then we also have the carbonyl. And we see the carbonyl stretching here. Our carbonyl stretching is around 1710. So this is the carbonyl stretch. If we zoom in, you can see that this is 1,500, this is 1,600, this is 17. So this is right around 1710 reciprocal centimeters for our carbonyl stretch of our carboxylic acid. So there's what you got to look for an alcohol and a carboxylic acid. What if we go to B? Remember that if we're trying to identify an alcohol or a carboxylic acid, we can draw a line at 3,000. Do you see any broad stretching up here? No broad stretching. stretching. Therefore, what would we call this? We would call this neither or neither. That is not a carboxylic acid and it's not an alcohol. What about D? Could anybody tell me if this is a carboxylic acid, alcohol, or neither? Absolutely. Absolutely. No stretching. We'll hear no oxygen, hydrogen stretching. Stretching. Therefore, neither. And let's go down here. What about E? What do you think E might be? We get something around here. This is from around 3100 to maybe around 3600, roughly. Yeah, absolutely. This would be an oxygen hydrogen stretch. So that means that this is an alcohol. We could also say that here's 1700, no carbonyl. Therefore, we know for sure it's not a carboxylic acid. Good. And then the last one, F, what do you think? What about F? What functional group? Absolutely. All right, we have so much broad stretching here. This is the oxygen hydrogen stretch. And this is the carbonyl. And so this is a carboxylic acid. Carboxylic acid. There you have it, folks. So there's your first problem. Distinguishing between an alcohol, a carboxylic acid, and neither. Let's try a different problem. Now we want to distinguish between a ketone, so a ketone, an alcohol, a carboxylic acid, a primary amine, and a secondary amine. So we've got 5 different functional groups. Let's see. Let's zoom in on A. So we'll start with A, and we could draw that line at 3,000 reciprocal centimeters right here. And you see that we have no stretching above 3,000. So we can say this is not an alcohol. It's not a carboxylic acid, not an amine. None of those things. What were the other possibilities? A ketone. So it's not an amine, it's not a carboxylic acid, and it's not an alcohol. Could this be a ketone? What stretching would we look for in a ketone? Well, in a ketone, if you go back to our table, it says that you would find carbonyl stretching at 1715. Let's zoom in. Let's take our ruler. We have 1500, 1600, 1700. This right here is 1715, roughly. So that means that this is the carbonyl stretching of a ketone. And so there's our answer. We have a ketone. Is everyone with me on this? On how I found out that this is a ketone? Okay, stop me if you have any questions. Don't be shy. Let's move on to B. I'll just throw that out there to my students. I think my students could answer this faster than me. What do you think? Alcohol? Ketone? Amine? What do you think this functional group might be in B? Yes, absolutely, Tracy. Yes, absolutely. This is a broad oxygen-hydrogen stretch. It's a carboxylic acid. This one goes from around 2,400 to, excuse me, around 3,300 reciprocal centimeters. And here's my carbonyl. If you look at the carboxylic acid, it also says that you have carbon-oxygen single bond stretching from 1320 to 1210. We zoom in here and bring the ruler. This would be 11, 12, 13. So that means that this stretch right here, this one is our carbon-oxygen single bond stretching. So this is a stretch, and this is a stretch here too. And if you're still unsure as to what I'm talking about, look, if we draw a carboxylic acid, the whole functional group, like this, This is the oxygen-hydrogen stretch. This is the carbonyl. And then this is the carbon-oxygen stretch here. Let's try a couple more. Now this one here I'm going to have to help you with. I'm going to have to help you with C and D because we haven't looked at a lot of amines yet. So what I'm going to do is I'm going to draw a line at 3,000 for both of these. So that's going to be somewhere around here. So here we go. Here we go. And then we're going to look above 3,000. Now here you can see that there's a broad stretch here. Kind of like, you see how that's kind of like one thing coming down? Look, it kind of goes like whoop, like that. It even makes that sound, right? It kind of goes like whoop. It's kind of a broad stretch here. And if you look at the one below it, it kind of has like 1, 2, like that. So what these signify, if you look at where these absorbances occur, this one is around here, and the one below it is around here and around there. So let's take a look. This first one is around, so this is 3,000, 31, 31, 32, 33. So this one is about 3250 reciprocal centimeters, and it's one broad stretch. And so this would be a secondary amine. So that is a secondary amine, right? Because in a secondary amine, you have one nitrogen-hydrogen stretch. This thing right here, this is your nitrogen-hydrogen stretch here. Whereas in a primary amine, oops, let me move that down. This one here is a primary amine, right? Because you've got two nitrogen-hydrogen bonds. Okay, you've got two of them, and then you've got two signals for symmetric and asymmetric stretching. So symmetric plus asymmetric stretching. Now, if you're asking me which one is the symmetric and which one is the asymmetric, I'm not sure. So don't worry about that. But this is what a primary and a secondary amine looks like. Not nearly as easy to recognize as an alcohol. All right, let's move on to the last one here. This is, oh, no, there's two more. So what do you think of E? What functional group might there be in E? Anybody have an idea? If we draw a line here, 3,000. Oops, I didn't mean to do that. So we can see there's no absorbances up here. So not an alcohol. It's not an alcohol. It's not a carboxylic acid. It's not an amine. It's none of those things. Absolutely can. But we do see the carbon-oxygen double bond stretch. So this is a ketone. There we go. A ketone. And the last one, I'll just throw that out there to my students. Anybody have an idea about this one? What do you think this might be? Absolutely. Absolutely. This is an alcohol. You see the broad OH stretch. And then this is the carbon-oxygen stretch. And so this is an alcohol. Right, if we write down the structure of an alcohol, this is the oxygen-hydrogen bond, and then this is the carbon-oxygen bond. If you look at the table, you see that an alcohol has carbon-oxygen stretching around 1,000 to 1,250, so this fits the range. And then, of course, our oxygen-hydrogen stretching is around 32 to 3650. And that is how you use the table. You can see that I have one more problem in here, which it just says match each compound with the appropriate IR spectrum. I'm going to save this I'm going to save this question for tomorrow, and we'll tackle it then.